Determining limits of two variable functions were in section 15.2. Now we're going to basically study the limits that we cannot do direct substitution in. So let's look at this example. Example 3, let f of x and y be xy divided by x squared plus y squared. And we want to evaluate the limit as x and y approaches 0 and 0 of f of x and y. Let's see if this function is elementary. Is this elementary? If I plug in, it is an elementary function, but is this part of the domain? If I plug in 0, 0, I get form 0 over 0, so form is 0 over 0. Therefore, it's not an elementary, it's not a direct substitution. It's an elementary function, but it's not part of the domain, so it's not a direct substitution. What do I do? And so as we go, you get a little bit more and more seasoned in recognizing what to do when it's, let's say, form 0 over 0 or indeterminate forms. But right now, first thing that we suggest is to go through different paths that you think are going to give you different numbers and say, so limits, if you remember, we said the limit over each path should be the same, right? Because when you plug in the paths, parameterize curves, then you go back to the one variable limit and you can evaluate even indeterminate forms. And so now we're going to do that, basically. Evaluate using plug-in paths first to see if it works or not. So the first path that I suggest is along y equal to 0. Y equal to 0 is a path, basically. So basically, I can parameterize this path by x equal to x and y equal to 0. And I plug it in. When I plug it in, it ends up with f of x times 0 divided by x squared plus 0. F of x and y is going, f of x and 0 is going to be equal to x times 0 over x squared plus 0. So again, we're going to plug in, the path. For x, we plug in x, for y, we plug in 0, and we end up with this function. Now, what is the limit of this function as this path approaches point 0 and 0? We're coming from on the x-axis, right? So the limit only depends on the t, which is t in here is x. As x approaches 0 of 0 over x squared, but the function is always 0 at any point but 0. Therefore, the limit of 0 is going to be 0. So that's one limit on this path is going to be 0. Now let's try another path. If I can find another path that doesn't have the same limit, I can say the limit doesn't exist. If I keep finding paths that have the same limits, I may start thinking whether or not the limit exists or not. But it doesn't prove anything. So that's the thing, and you get seasoned again, and you kind of recognize what limit exists or not. Now let's try another path. This time, let's try y equal to x. What does that mean in terms of? So plugging in path y equal to x. So limit, and since the parameter is x, as x approaches 0, the point goes to 0, 0 of the function f of x and x is just because f of x and x is 1/2. So f on the entire path is 1/2. This is going to be 1/2. Oh, so I found along this parameterized path, limit was 0. Along this parameterized path, limit was 1/2. Can limit exist? No, because every parameterized path should give you a value, and those values have to be equal to each other. So the limit does not exist. Now it's interesting to look at the graph of the function. So the graph of the function, as you see, what was this parameter, the parameterization? It was y equal to x. Here, y equal to x is their paths that go along here, right? You can even draw it if you want to. That's the y equal to x. And so you're expecting to get 1/2 there. But as you approach along y equal to 0, that's x-axis, as you approach here, you end up with value 0. And it seems like it from a lot of places. If you approach, you end up with 0, and in a lot of places you approach and you end up with 1/2 and other values. Anyway, so this is not continuous because it's just there are folds, and those folds do not end up at the same place as they approach 0. I usually recommend to look at the GeoGebra applet for this. You see that the fold at y equal to x, you can see it better here. Do you see there are always a little bit disturbance there? It's because and it's even worse for the slides, because the programs that run it, they start basically complaining, why are you getting so much close to dividing by 0, or why are you getting close to not having a limit? And so the disturbance is just meaning that. But you can see that even for y equal to negative x squared, you can see that the function actually approaches negative 1/2. So if the path was not y equal to x but y equal to negative x, then the value would be exactly negative 1/2. And you see that here is value is 0 for us on the x-axis or y-axis. So these are some interesting part that viewing it in person helps a little bit with understanding it. Again, the limit does not exist in this case because these two values are different. Now, so in determining limits of two variable functions, general principle for it is, in order for limits as x and y approaches a and b of f of x and y to be equal to L, the function f of x and y must approach L along all paths approaching 0, 0. If any two curves disagree, then limit doesn't exist. But big warning, this is huge. Be careful. You cannot show that a limit exists by showing that two specific curves agree, because there could be a third one that disagrees. It might be hard to find. Again, you get seasoned and you figure out, oh, this is fruitless. But how it is that there are other methods to show that limit exists. Not this method. No, you cannot just say two curves agree and therefore limit exists. Even showing that infinitely many curves agree might not be enough. And so the next example is just that. So let's say example 4, limits of g of x and y equal to x squared over x squared plus y squared, and evaluate limit of x and y approaching 0 and 0 of g of x and y. So let's go with one path that approaches 0 and 0 as and so that could be path x and x basically. So let's go along path x equal to y or y equal to x. That means you replace y by x in here, and so the parameterization is with respect to x, and then you plug in x in here to find the g of x and x. So g of x and x is x squared divided by 2x squared, that is 1/2. So the limit is 1/2. Now how about along x equal to negative y? Again, plug in, this time parameterization is x and negative x. And so you plug in and you end up with 1/2 again, because negative x to the power 2 is x squared. And basically, and yes, negative x over here to power 2 is x squared, and so you end up with the same answer. Is it true that this function has a limit as x and y approach 0 and 0? No, actually it's not true. Here a third path that tells you that it's not true. So let's have y, let's approach from parameterized curve y equal to 0. That's actually the x-axis. So what you plug in is x and 0, and the limit is going to be x squared over x squared, which is 1, and these two are not the same as this one, and therefore the limit does not exist. So just because you found two that have limits doesn't mean the limits exist. And so here's the picture of this one, and you can see that at some points there are creases on the curve as we approach 0 and 0, and those creases sometimes go to 1/2, sometimes go to 1. Now let's look at the link and see what it gives us. Okay, so this is the graph of it in GeoGebra, and you can see that as we're approaching through y equal to 0, it becomes 1 as we're approaching y equal to x or y equal to negative x. It's smaller, and basically you can show as you're approaching one direction you get one value, and this is the y equal to x or y equal to negative x, and you get other values. So different creases will give you a different value basically, or different parameterization will give you a different value. And then you can see at x equal to 0, which is the y-axis, you approach 0. At y equal to 0, which is the x-axis, you approach 1, and then the other two are somewhere in between, and so there's no limit in there. It looks less disturbed, but different calculation basically has less or more bearing on the computational program. Now we're delivering that one function, or there are multiple functions that have this property, but that you can easily show that infinitely many curves agree on the limit, but still the function does not have a limit because there is a curve that doesn't agree with that infinitely many curves. And so here's the function g of x and y is equal to x squared times y over x to the fourth plus y to the second. And so evaluate limits of that as x and y approaches 0 and 0. And in something that I have to go back and make sure that we remember, these are elementary functions, but 0 and 0 is not part of the domain again, because if I plug in 0 and 0, I see that the form is again is 0 over 0, and that is why we're investigating other methods. Basically, if I could do direct substitution, I would have done direct substitution. I thought maybe we should repeat this. So if there's no direct substitution, so you have to figure out, first of all, are there two curves that the limit disagrees on, and so on and so forth. So what are the values that may actually work for us? And so one way is using the curve, which is a line y equal to mx. So g of x and mx is going to be equal to x squared times mx divided by x to the fourth plus y squared, and this is mx to the third. Oh, y squared should be what? Y squared should be now mx to power 2. mx to power 2. So what you get is x to the power 4 plus m squared x to the power 2. Let's try to, I know that the reason we're getting 0 over 0 is factors that are approaching 0. So let's try to factor those out. And so I get x to the power 2 out of the numerator and x to power 2 out of the denominator. Out of x4 remains x squared and m2, and then these two are going to be simplified, and so you end up with mx over x squared plus m squared if x is not equal to 0, which in here technically it's not. So now I'm finding the limit of the curve as x approaches 0 of mx over x squared plus m squared. And one more thing, we assume that m is not equal to 0. And so here I see that numerator is going to be 0, but denominator is non-zero. Therefore, the entire thing is going to be 0. So for every y equal to mx, whatever m you want to put in, you can put in 2, 3, 5, 10, 200, whatever you want to put in, the limit over the curve y equal to mx is going to be 0. This seems like infinitely many limits that are 0. Does this mean that the limit of the function is 0? So suspense continues until we find one more curve, that is y equal to x squared. So this one was a little bit harder to guess, right? Because if you had found y equal to along y equal to x, or along y equal to 0 or x equal to 0, you would end up with 0 again also. Now, y equal to x is a little bit harder to guess, but when you plug it in, basically you end up with f of x and x squared equal to x to the 4 divided by x to the 4 plus x to the 4, which is just 1/2. So this one does not have a limits neither. All these methods that we try to find out no limits for, you're starting to kind of get this. When you're trying to find no limits, you basically want to make either the degree of the numerator equal to or less than degree of the denominator. And what do I mean by degree? It's you want to degree is when you add up all the exponents of each term. So what you did in here is y equal to x squared, and that made the degree of numerator 4, which would match the degree of the denominator. And then so you get a value that is different from just plugging in x equal to 0 or y equal to x or so on and so forth. And so that's the trick with this type. And in the previous examples, let's go back to previous examples, you saw that the degrees were the same. So all you need to do is just do y equal to x for that one. And then y equal to 0 would work also. And so two curves would be given to you. Over here, the degree of top and bottom are the same. So you tried y equal to x and x equal to 0 and y, or y equal to 0. And in here though, when the degree wasn't equal, the tricky curve was y equal to x squared. And that gave you the right answer. Now let's go to the link and see the... So the picture in here is a little different. Can you tell that the crease has a parabola shape? So there's a crease with a parabola shape, and that's the cool part. And that's the curve that will give you a different value. It's right there. The crease is a parabola shape, and it goes to 1. Everywhere else seems like a lot of things are going to 0. And there's another crease that goes to -1. That's the cool part. Again, one program that you looked, the disturbance was minimal. You can see that the program that we used to create the pictures within the slides it has a little bit more disturbance, but you still can see those parabolas, y equal to x squared or y equal to -x squared. I got here question 15.2b. Which of the following pairs of paths in the xy plane shows that the limit as x and y approach 0 and 0 of xy over x squared plus y squared does not exist? Again, it's one of those forms, 0 over 0 again, and we want to see if one of the, basically what it's saying is saying that find two paths that the value of the limit on those paths are going to be different. Now, I hope you took a break and figured out the solution, and so let's try. So in here, if I plug in 0 or for x, I get function 0 over y squared. And if I plug in 0 for y, I get 0 over x squared. Both of these functions, as x or y approaches 0, have limit value 0. So this one does not give you that the limit doesn't exist, because the two paths both give you the value for the value that works, basically, not two different values. Now let's do y equal to x and y equal to negative x. If I plug in y equal to x, so for y plug in x, I get x squared divided by x squared plus x squared. If I plug in negative x, I get negative x squared over x squared plus x squared. And so 1, as x approaches 0, approaches 1/2. The other one approaches negative 1/2. And so this is a good deal, because then I can use that to show that the limit doesn't exist. Two different paths gave me two different values. So what about part C and part D? If you plug in the values then and simplify x squared for C and x to the third for D, then you realize that basically the entire limit for both curves given in C and for both curves given in D are going to be 0. So it doesn't give us any information. Basically all of those other choices are useless. And so next video is going to discuss how to find if the limit exists. So far we did how to find the limit doesn't exist when we have the form 0 over 0.